So thank you also for this very kind invitation. So if I understood, if there is the alarm, is for me, no? It's a subliminary message. Okay. Okay, so today I would like to introduce this work. It's a joint work with Eric Schegel from UTS, with his PhD student, Messias Alpheus. It is about multiple curve consistent modeling, and it is quite different with respect to the classic approach to model a multiple curve time structure, in the sense that we will try, as we will try to develop later, we'll try to introduce some consistency between the curves. Now we cannot speak about discounting. We have in forwarding curves, we have to deal with the different tenor specified by, for example, 3 months, 6 months, and whatever. And normally people take just these curves from the sky and do not really enter into details in terms of giving a consistency if you want to go across curves. So in principle, it gives to some non-very parsimonious models, in the sense that for n curves and tenors, you should consider, in principle, at least n risk factors. So we would like also, in order to keep parsimony of the model, to make some consistent approach in order to communicate, let curves communicate each other. Okay, so the agenda. We will speak a little bit about the reason why we are speaking about multiple curves nowadays, because of course after the financial crisis there are new effects, new Stiglitz effects that you should be able to describe. And the fact that in principle there exists some potential arbitrage opportunity in the market that people do not exploit, so it was our first motivating point, why quants do not exploit this apparent arbitrage opportunity in the market. And it was really a crucial example, and I think that if I will be able to explain this potential arbitrage opportunity, it is the most important thing on my talk that you should retain. We will give an alternative way to describe this phenomena in order to get rid of this potential arbitrage opportunity, and it will lead to a consistent framework for the multiple curve modeling. The model we will use in order to describe and also estimate and calibrate with market data is just instrumental, in the sense that we keep things as simple as possible in order to be able to calibrate, we can say numerically speaking, quite easily. But okay, theoretically speaking, you can sophisticate a lot, much more the model, and we are still also thinking about other potential models in order to describe our techniques here. And then finally, I will give some very preliminary calibration results, in the sense that there is much work in progress research. Okay, so first of all, the motivation. So after the financial crisis, of course, there are some new effects that maybe will remain permanently. So the fact that now there are some basis spreads and basis swaps quoted with the presence of a spread that were neglectable before the crisis, and even after the crisis, they keep non-neglectable levels. So, which means that basically we have to deal with this kind of new effect that we are going to show in a moment. It seems to fight with the classical absence or arbitrage opportunity principle. So we need new mathematical tools and new rules in order to describe this kind of new situation. So in order to give a specific example, we consider a particular product in the market, which is called the frequency basis, so a tenor swap. A tenor swap is a double floating leg swaps, in the sense that you can exchange two floating legs, but with different tenors. So keep in mind the example 3 months against 6 months, for example, swap. So typically what happens in the market nowadays is that this kind of product is quoted with the presence of a spread. So in order to exchange these two tenors, you have to add, typically to the shorter tenor rate, a spread, a constant spread. And this is the way in which market quote this kind of product. But according to the no arbitrage principle, this spread should be equal to zero. Before the crisis, this spread was very, very neglectable and it was completely cancelled by the transaction costs. So the bid-ask did not allow for the possibility to exploit this arbitrage opportunity. But during the crisis and also after the crisis, even including the presence of transaction costs, and there is also an empirical study of Chang and Schegel, this spread cannot be explained or eliminated by transactions. So there is still a permanent, persistent presence of this kind of spread, which contradicts the no arbitrage principle. So perhaps this is just an example in order to understand that in the market now, there is this spread that during the crisis and according to the maturity of the product can be really important in terms of basis points. I mean, its business is not just an imperfection. So you can arbitrage another counterpart if you are able to deal with this kind of potential opportunity. So in order to describe this arbitrage, I keep things very, very simple, and I consider a stylized example. So I would like to construct this arbitrage opportunity by replicating the linear products that I'm using now in this example. The first position in my portfolio consists, for example, in a basis swap. So I take a long position in a basis swap, which pays a LIBOR 6 months and receives LIBOR 3 months. So I consider a long position in the LIBOR 6 months. What does it mean? I take just the possibility to buy LIBOR and I pay back the corresponding payoff. Same position, but in the short part in LIBOR 3 months. And I take a rollover of this kind of position. So at each 3 months, I roll over my borrowing position. So using this strategy, in principle, should happen that I get the presence of the basis spread with the corresponding apparent arbitrage opportunity. So let's specify in detail the situation. According to the position in the basis swap, I just consider the 3 involving times, so the initial time, the signature date, if you want. And then it's just stylization in order to be coherent, very close to the market practice. I mean, I should modify a little bit these cash flows, but basically it's financially meaningful. So in 3 months, due to the basis, oh, sorry. Okay. So the cash flow associated to the position on a basis swap consists, okay, it's costless, so there is nothing at the beginning, 0 here. And then I exchange, as I told you before, 3 months, every 3 months, LIBOR 3 months, against LIBOR 6 months. So I have this cash flow in 3 months. I have another cash flow involving the LIBOR 3 months in order from 3 months till 6 months. And then the final cash flow involving the LIBOR in order from 0 today till the end. Okay? So basically there is a spot LIBOR 3 months here in the first cash flow. There is, if you want, a forward, the future value of the LIBOR negotiated in 3 months in order for the second quarter, and then the cash flow involving the LIBOR. This is the cash flow due to this linear position. Well, so the idea is that I would like to replicate, in some sense, in the opposite sign, this kind of strategy. So I take a long position on the LIBOR, which means that I have a cash flow, I have a cash flow equal to -1, so I jump lending, so I pay the instrument now. And what I get at the end is just the LIBOR over the interest. So what I paid at the beginning, accrued by the corresponding interest. Okay, this is simple position according to the long counterpart. And now I replicate with a short position the intermediate cash flow, in the sense that I'm short in the position in the LIBOR 3 months, involving so the presence of this cash flow, intermediate cash flow. I should write here -1 over 4, blah, 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 but this -1 disappears in the sense that I roll over the position till the next period. So I get 1 at the beginning, and borrowing and rolling over the position, I have the possibility to replicate this intermediate cash flow. Pay attention, in the basis swap, as I told you before, the market convention is to quote this product according to the constant basis spread, okay? So this leads to the apparent arbitrage opportunity, because if you count all the cash flows, what remains in the strategy is something which, whatever sign C, but typically C is positive, leads to a potential arbitrage opportunity, okay? And this contradicts basically all textbooks in finance. So the idea is, if it is possible in a so easy way and so simple way to get an arbitrage opportunity, in principle, quants should exploit this arbitrage opportunity. So it's important to understand which is the problem, underlying the fact that people do not exploit this basis spread. And the idea, the intuition should be quite clear, in the sense that if a counterpart has the possibility to borrow at LIBOR with maturity 3 months, so according to this position, of course, it's not said at all to be able, once again, to get the same market condition, so to be able to borrow for the second sub-period at the same condition. That's the idea. So it may be that I'm able to borrow at this condition because I'm a representative element of the panel, consisting in the LIBOR, basically. But it is no longer true in 3 months because, for example, I have a downgrade risk, or I have a shock in my funding condition, for example. So there are some liquidity problems, basically, funding, which can be different according to sub-period to sub-period, or I have a downgrade risk due to the fact that, to be honest, I should also speak about upgrade risk, in the sense that the panel, you should plot a box plot, in the sense that you cut off all the lowest percentage, also the highest percentage, and you take the average of the middle part of the panel consisting in the LIBOR. Which means that if I have an upgrade of my rating, maybe I also go out from the representative situation of the LIBOR. In any case, I can face a potential Rollover risk, in the sense that I no more representative member of the LIBOR. That's the idea. And there is, if you want, another philosophical question to ask. What is LIBOR? What is LIBOR is not clear, in the sense that there is no bank which is 100% representative of the LIBOR panel. It is just an average, if you want. And there is also another political question to ask, in the sense that LIBOR can be manipulated for speculative reasons and whatever. And this is also the reason why maybe I hear the wind about the possibility to replace LIBOR with something less manipulable, for example, the repo rates or something similar. But in any case, this is nowadays the situation. So if you want to deal with the possibility to have a renewal risk or funding risk, in the sense that our funding condition may move over time, is no more clear to be able to exploit this arbitrage opportunity. I mean, there is no arbitrage at all. There is just a potential arbitrage only if I'm sure about my future funding situation, which is not the case. Okay, this is basically the idea. It was the starting point of our research. Well, so before the crisis, there was just one curve in order to discount and project future cash flows according to yield curve, whatever tenor. After the crisis, now we face a segmentation of the market according to the particular tenor we are dealing with. And in particular, rates with different tenors display a priori in principle different dynamics, so just partially correlated. And this is also reflected by the spread that we face and we realize in the market. The typical example, for example, is between LIBOR and the overnight rate and swaps. Well, so the idea is it possible to include some extra risk factor in order to describe the two main reasons for which we have this apparent arbitrage opportunity? So funding, liquidity risk, and downgrade, or if you want, renewal risk. So our idea was to model directly these risk factors by giving, for example, a dynamic. Can be whatever, as I told you before, it's just instrumental, the model we are going to use, but it is that, okay, is it perhaps possible just with two sources of risk to describe the whole situation and also market segmentation? If it is possible, it would be interesting because implicitly it leads to a very parsimonious model, in the sense that whatever new tenor or new curve you introduce in the model, you still use the same number of factors. That's the idea. And what is more, sorry, I'm too Italian, my gestuality. And what is more, there is the possibility to make a connection across the curves. Okay, so they do communicate each other. Well, what happened in the literature? But typically, there were two main approaches. The first one, what we decided to denote as a pragmatic approach, means that, okay, we take curves just as exogenous, in the sense that we realize that there are different behaviors according to the different tenor. So, as a matter of fact, we introduce an additional risk factor in order to describe the additional tenor. And there are many contributions in this direction. I also contribute a little bit in this direction. So pragmatic approach means that we don't try to explain the reason of the existence of multiple curves, and basically we lead necessarily in whatever model, short, Higero-Mortel, LMM, to introduce n risk factors according to n desiderata, so number of curves, for example. There are also other approaches which are denoted in our notation as fundamental approaches, in the sense that they try to include or give some economic intuition and reason in order to justify the existence of the different curves and basis spreads, etc., etc. So up to my knowledge and understanding, Morini was one of the main contributors in order to give some economic intuition about this existence. And the key reference is the paper of Damir and Troll, where they try really to give also some model in order to describe explicitly the renewal risk. So in terms of renewal risk, our approach is very, very similar to the paper of Damir. But there is something different in the sense that in their paper, very interesting, not just because Dan is in the floor, but it's really very interesting. There is still some missing in terms of liquidity, because at the end, after all, we see that there is a not very specified or well-determined liquidity risk factor. That's the idea. So our purpose here is to really give a name to this liquidity factor, so that will be denoted as a funding risk factor, and give also dynamics to this factor. And in order to be able to link this factor with observable things, because our ending aim basically is to be able to calibrate with real quoted data. That's the idea. Well, so the idea is that we would like to explicitly model not only the rollover risk, so the downgrade or upgrade, but what we denote with rollover risk, so the risk due to the fact that it's not obvious to get the same market condition in order when as soon as we roll over our position, is also related to the presence of a potential funding liquidity risk, so difference in our market conditions. And we would like to drive our basis spreads, the quantities which are quoted in the market, with these two risk factors. That's the idea. As I told you before, if you are able to do that, should be in principle very interesting, because this reduces the dimensionality of the model, of the market. Okay, so sorry. Okay, so the idea is the model in principle should be more parsimonious and is very, very similar to what people did in risk credit, in the sense that it's very similar to the reduced form approach. In the sense that, okay, we don't really give a clear economic intuition about the structure of the credit risk, but still we are linking with a so-called intensity-based approach. And I anticipate a particular important comment is that in the intensity-based approach, the analog of the short rate, in particular the overnight rate, is not necessarily something which is safe, which is not observable. And that is that what typical people do in multiple curve literature is to consider the overnight rate as a proxy, basically, of the risk-free rate, in the sense that the tenor is so small one day, that is okay, should be considered as a good proxy for a risk-free rate. This is not correct in the perspective of a reduced form approach in the intensity-based literature, and also in our approach, we don't really need this kind of approximation. Another comment from the market. So there is a very, very high sensitivity with respect to this problem, especially in Australia, when we spoke with some quants over there, on the possibility to have some not only default risk, but also rollover position. There is another problem. For example, in other countries, I have in mind the example of South Africa, for example, and for this kind of market, very active in interest rate products, for which there is no OIS, there are just a LIBOR market. And for this market, for example, it's very important to have a consistency across the curves, because you cannot use the proxy of the risk-free in this case, and also you cannot really exploit the possibility to communicate between curves. So if you're able to introduce a consistent model, we can at least, in some sense, recover the behavior of something with a different tenor with respect to what we use in order to calibrate our model. In other words, if you calibrate using 3 tenors, you are able to forecast and also deduce some properties of non-calibrated tenors, which is potentially interesting. Well, so the idea is we consider with the overnight rate, which is just an abstraction in the short rate specification. So RC denotes the overnight rate, and the overnight rate consists in something which is really risk-free. I told you before, we are not considering the overnight rate as a proxy for the risk-free. It's something which is risk-free, which does not exist, but here, yeah, it makes sense to consider a proxy, and the proxy fixed in mind is just the repo rate here, plus something which involves, in some sense, a global, systemic default risk, which represents, if you want, the average default risk of the panel consisting on the list of the LIBOR banks. So the overnight rate is given by the short risk-free rate plus something that, according to the possibility to consider recovery or partial recovery, etc., you have this kind of specification for the overnight. Okay, so capital lambda denotes the global, if you want, the panel or average aggregated default risk of the panel. Okay, it's already developed in the sense that we don't need to assume that the RC, the overnight rate, is necessarily free. What is important to understand is that RC, on the contrary, can be used as a discounting rate. It is simply given by the fact that it is the collateral rate, if you want, already suggested by the ISDA credit support annex, so it should be quite innocent as an assumption, the possibility to use this particular rate as discounting factor. Okay. So we consider the corresponding discounting factor, so if you want the zero coupon bond according to the overnight rate. We don't enter into details about the quite problematic issue on the existence or uniqueness of the risk neutral probability measure in this market. We just keep as an exogenous fact. So we are already working under the risk neutral measure Q, and we consider also the discount factor of the OIS rate. So what we are going to introduce now is the rollover risk as a forces, and this consists in a part which is a pure funding liquidity risk, so the possibility to have different market conditions, or the possibility to have a downgrade or upgrade risk, so related to, if you want, a credit spread over the overnight rate. So this is the rollover risk, which is a superposition of pure funding as pure, if you want, credit risk. So small lambda represents, if you want, the specific idiosyncratic risk of a member of the panel, which is at the beginning representative element of the panel, but it can follow a different story along its life. Okay, so I take at the beginning a representative but specific element of the panel, and then I observe the behavior in terms of default risk, which is different with respect to taking the average of the panel situation, which is represented by capital lambda. So capital lambda is the systemic, if you want, systemic risk of aggregated default intensity. On the contrary, small lambda represents the idiosyncratic specific default risk. And my idea is that I take a representative element at the beginning and try to see what happens. Okay. At the beginning, small lambda is equal to 0 for the same reason. So at the beginning, I take something which is representative. So the initial condition for lambda is quite clear. The boundary condition is clear. And then whatever may happen. Okay. So now we would like to repeat the same potential arbitrage opportunity as before, but with the additional presence of these two new risk factors. So the idea is that instead of considering 3 months, 6 months, I consider a basis swap involving the OIS against the LIBOR. So the first position requires the borrowing overnight, so at the overnight rate. So if I borrow overnight, what I get as a cash flow is the initial cash flow equal to 1, and then I have to give back the interest, and the interest overnight involves also the presence of the rollover risk. So including idiosyncratic together with the funding risk. So this is what I have to pay at the end. Now, if I discount according to the ISDA annex, I should consider the overnight as a discounting. So if I take the present value according to the risk neutral measure, this is the quantity I get at the beginning. The second operation involves the OIS, so a spread involving the overnight, which is costless at the beginning. And then I get the exchange. This is a stylization. We will see in the dynamic framework what I should change in order to be consistent with the market practice. But the idea is that if I stylize, there is no intermediate cash flow between small t and capital T. So this is the exchange of the two floating rates given by the fixed rate I pay, OAS against the interest given by the overnight interest rate. So 1 plus something is given by the corresponding interest rate. So the exponential of the integral of the overnight rate minus 1 represents the real interest I have to pay. Once again, I discount with respect to the overnight rate, and what I get is this expression, basically. Okay? So if I discount with respect to the overnight, basically I take the same exponential with the minus, and I get, in any case, a very simple formula, because all products here are linear so far. Okay, now I consider the position on the LIBOR market, and the LIBOR market gives this payoff here. So I take the lending point of view, so I pay minus 1, and I get back the interest at the end. Discounting once again, but including the possibility to have also the idiosyncratic risk, because here I'm lending, I get this amount of money at the beginning. Okay, now the cost of the whole strategy is equal to 0. So in principle, I should equate all the discounted, the present values of the cash flows, and this is the equality I end up with. So I get that the expected value of the term involving just the pure funding risk is equal to this expression. And now some considerations are in order. Because, for example, if I consider that there is no risk for renewal or refreshing for the panel, it means that lambda is equal to 0, then I'm able to explain the spread between the OAS and the LIBOR just in terms of the funding liquidity risk. But the important thing is that there is no more arbitrage opportunity in principle. I mean, it's not obvious to exploit this arbitrage opportunity. In any case, you have that the spread, you see the difference between the LIBOR and the OAS rate can be explained in terms of something which involves explicitly the presence of the pure funding risk. Also, of course, as we decided to take as a discount factor the OAS rate, the overnight rate, basically I have an expression involving the OAS fixed rate with the discount factor. The relation is as before the crisis, basically. So this implies that I have this equality involving basically, so the financial meaning of this equality means that if I project and I discount the overnight rate, I get exactly the symmetric relation. So forwarding and discounting is symmetric, basically. This is no more true for the LIBOR, and this is, of course, well known after the crisis. But what is interesting to know is that even if I introduce the additional presence of default risk, so the intensity due to the default or downgrade risk, is still not true that forwarding and discounting is symmetric, because here I'm neglecting the possibility to have a difference in funding risk. In other words, this equality holds true only if there is no funding risk. In the presence of funding risk, I mean, there is a missing risk factor in my argument. That's the idea. Okay. So it may be considered as a counterintuitive equality in the sense that including funding risk is quite unusual. But if you want to consider also the possibility to eliminate this arbitrage opportunity, this is mandatory. I mean, is necessary. Okay. So what happens in the case where we consider the general situation, so where there are also intermediate cash flows due to the fact that the overnight, the OAS pays also in the meanwhile. I don't want to bore you too much, but the idea is that, okay, you can repeat the same argument by introducing also intermediate payments, and everything goes well in the sense that you are able to repeat the same exercise, and you end up with very similar relationships, and the idea is that you end up with the formula involving the LIBOR, which has to be capitalized, which has to be exponentiated to the number of sub-periods, basically, but still you have the same representation in such a way that this quantity cannot be equal to 1 unless there is no presence of the funding risk. So you have just to modify a little bit the powers here in order to repeat the same argument also with the presence of an intermediate stream of payments, a stream of cash flows. Well, so you end up with exactly the same equality as before. Notationally speaking is perhaps more heavy, but I mean the financial meaning is exactly the same. What is important to understand is that now you can replace the definition of the OIS fixed rate in terms of the stream of the OIS discount factors. This is exactly what happened before the crisis for only one LIBOR. We can still repeat the same argument for the overnight rate, so we can have the same relation linking the fixed rate in terms of a swap. But if we replace this expression in the equality before, I end up with this expression for the LIBOR. In other words, in our model, it is possible to add the LIBOR ex post. I mean, the LIBOR is an output of the model. In particular, the expression of the LIBOR involves the presence of some expectation or conditional expectation involving our two main risk factors. The pure funding risk and the idiosyncratic are also systemic, included in the overnight rate risk factors. So now we are ready to introduce a stochastic model, in the sense that the desiderata is to be able to get closed form or analytically tractable properties for this kind of object, because all these contracts will be written on this kind of rate. Okay? So, and the natural candidate, of course, if you look at this expression, of course, the natural candidate is, for example, to start with affine processes. But I mean, it's not mandatory. We are still investigating other possibilities for the moment. Well, so once again, I repeat, because perhaps this is the most important result, we don't start with the dynamics for the LIBOR. The dynamics of the LIBOR is an output of the model. You just take Ito according to your particular choice of the model specification for the risk factors, and you have the corresponding process. Maybe the dynamics is not so friendly, we don't care. We don't care, because in any case, we can express everything in terms of the corresponding primary risk factors. Well, so if you want to calibrate the model with market data, basically you should be able to find market prices quoted in the market on the right-hand side, and the left-hand side, formulas involving for us linear products. So we have a very liquid market for basis spreads. And so we deduce the corresponding parameters of our model by imposing a system with different maturities and different tenors. This is the matrix we give as an input in order to calibrate the models. So, model specification, as I told you before, the choice of the model is just instrumental for the moment. Just keeps things simple as possible. So I consider, for example, an affine specification of our model. What does it mean? It means that we are considering three building blocks: the overnight, the small lambda, and phi, as projection of a certain multifactor specification of an affine process according to different directions. So typically, in order to keep also the calibration quite simple, the vector of the projection would be chosen to be constant, but of course we have the possibility to consider deterministic time shift in order to be able to fit perfectly the initial curves, as usual in interest rates. So the idea is that we should have some constant piecewise but still deterministic changing constant parts, if you want, in the specification, and then projection along some directions. Well, I take, for example, a fine process, Higgs. So here there is, of course, the usual specification for a generic affine process. You can consider, as we did, Koch-Singer-Soros, because it leads to very, very explicit constraints in order to grant, for example, positivity. due to failure condition, etc., etc. If you change the model, for example, you can take the state space domain to be equal to the positive semi-definite matrices, or so you lead with Wisher processes, you can exactly do the same thing, but here for the calibration point of view, the positivity constraint is not so obvious, so you have to battle a little bit in order to deal with the constraint that you have to impose in your codes when you're calibrating the model. So the additional value of the Wisher process, even in a very simple 3 by 3 dimension, is not so obvious. I mean, it's quite heavy, computationally speaking. So you consider just 3 independent Cox-Ingersoll-Ross, and then you mix according to the particular projection. Okay, so blah, blah, blah. I can skip this, which is just a recall of the affine methodology. You have something in terms of a Riccati equation. The important thing, which is just a pedagogical remark in order to understand what happens if you move from affine processes to something else. If, for example, you move from affine to polynomial processes, what you ask for is, instead of having an expression of the moment generating function of the process, or if you want here, the transition density in terms of the Laplace transform, which is given by an exponential affine form involving your affine process here. This is what you require. You can, for example, ask that the form of this functional is, for example, polynomial. Or you can ask something different. You can ask that the moments take a polynomial form. This is the classic approach for polynomial processes. And you end up with some constraints on the dynamics of your stochastic factors. Jacobi diffusion, one or multidimensional. So far, I didn't see any multidimensional Jacobi process calibrated so far, but in principle, you can consider also the possibility to correlate a multidimensional polynomial process, that's sure. What is less evident, and in my opinion should be more natural as an approach, is I'm not really interested in imposing the polynomial nature of the moments. I mean, instead of reasoning in terms of moments, I would like, for example, to impose directly a power here. So in terms of what I really need, which is the Laplace transform of the process, so the expected value of the exponential of the process taken as a photograph at a given time, I can consider the exponential of the integral of the process, etc., etc. So for affine processes, this is easy because in any case it's just a question to insert a term in the Riccati equation in the boundary or in the equation itself. But if you consider the possibility to have this transform in terms of already a polynomial, so a power of the corresponding state factor, the consequence in terms of the dynamics of this factor is quite different with respect to what you find in terms of classic polynomial processes. And in particular, in this case, if you push forward this technology, you end up with a process which may have a drift which is no more linear. It can be also quadratic, for example, and also a diffusion coefficient which is not necessarily the square root of a quadratic process like in the Jacobi case. You can go further and you can get, for example, power 3. Which in principle may give you some difficulty from the analytical point of view, but honestly, from the numerical point of view, is much, much faster. And in addition, you can avoid the problem that even if you know a certain number of moments, you still have the problem of reconstructing the corresponding density. You can, for example, project into I don't know, series development of Hermite or whatever polynomials, but you are obliged to truncate at a certain time. So you face the negativity issue of the corresponding series, and it matters in classic polynomial processes. In this case, if you impose not not the moments, but already the moment generating function to be polynomial, you have not at all, none of these problems, and in particular, there are very, very simple conditions in order to grant positivity of the result. So we are still, this is still a topic under investigation, but in my opinion, it's very, very promising in the sense that if you really want to extend or go beyond the affine class, in my opinion, is not obvious, it's not natural to take the classic polynomial approach. Perhaps there is something different which is more suitable for the particular interest rate problem. That's the only comment I would like to give now, so far. Okay, so in the case of affine processes, everything is very standard. You end up with some Riccati equations, and this is also possible in the particular case of, for example, Cox-Ingersoll-Ross. You have even closed form solution for this kind of equation and closed form expression for the positivity of the process. So no worries about the bounds that you have to impose in your code. Okay, so which are the quantities I'm interested in? Basically, in order to exploit the analytical tratability or the formula given the LIBOR, I have to consider a number of expectations. This is the first one involving the pure funding risk, the expectation involving the couple overnight rate and the downgrade risk, as well as the overnight rate alone. Okay, so in the affine framework, all of them are trivial in the sense that we fit exactly in the domain of affine processes, because all these expectations can be written in terms of the exponential of some solutions of Riccati equation. In the particular case where you have some more sophisticated problems like that one, if you plug the solution in terms of intermediate payments, you can have the problem of considering the solution of this guy together with the first factor, which involves different extremos in the integral. I mean, you apply the tower property and you nest the Riccati methodology 2 times, 3 times the number of times required by the problem, and you end up in any case to the exponential of something which can be quite complicated to write, but okay, from the numerical point of view, it doesn't make any problem. Okay, so step by step, we construct all the important expected values with this affine specification. We end up with very huge formula. You can imagine that as soon as you construct the swap, you have to deal with more and more involved formula. So the idea is that I just put here formulas in order to let you understand that you have to code with different lines of formulas, but everything is completely explicit. That's the important thing to understand. Okay. If you want to deal with no linear contracts, what happens in this case? Basically, you have the same problems as in the usual affine framework. So as soon as you attack the problem of computing the price of a couplet involving just the payoff of LIBOR against the strike, there is no problem in the sense that in the affine framework here, you can explicit the process in terms of an exponential of something involving the conditional expected values. So the idea is that this factor can be given in terms of the exponential of solutions of Riccati involving the state variable. This state variable is affine, so you can perform basically the FFT or the Fourier-based methodology in order to price the explicitly modulo Fourier integration, the price of a cap. Of course, for swaptions, the problem is different, and I completely agree on the remark on Damir, because in the linear rational model, swaptions, boom, are very, it's very friendly, the approach for this kind of products. In this case, you can find efficient bounds in the sense that the swaption in this framework but it's not just for this model, it's in general for an affine methodology, an affine approach for short rates. Basically, a swaption can be seen as a basket option, basically. And for basket options involving affine processes, there are very, very efficient bounds, okay, lower bounds and upper bounds. Still involving Fourier analysis, and the intuition is quite simple. You can approximate an average, an arithmetic average, so the sum of exponential of affine processes, arithmetic average of exponential with geometric average, okay? And taking the geometric average, it means that you have just one exponential of the sum of affine processes, and boom, this is very efficient to be computed. So the idea is that this approximation, arithmetic versus geometric, leads to bounds which are very, very efficient, but what is more, they are very fast to be computed. Okay, so for the blah, 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 this is just a comment on the pricing of some less evident contracts like swaptions, as I told you. Okay, so for our specification, we chose, for example, the Cox-Singer-Soros, very, very simple framework. So we have a projection of a common, we took first, of course, a three-dimensional process, so D is equal to 3. We took a three-dimensional Cox-Singer-Soros with independent components and different projection according to constant A, B, C, and eventually time-dependent initial constant terms. Well, so far we can, in principle, take as an input for our calibration the basis spreads quoted in the market. But in this case, I mean, it would be nice to be able to disentangle the pure credit risk with the funding risk. And this is possible. So in other words, I would like to calibrate, to filter for my calibration the lambdas with respect to the phi's. And this is possible by introducing additional products. In this case, the CDS. So the CDS gives a lot of information of the pure credit risk of the issuer, in particular of the member, representative member of the LIBOR. So we took the list of the members of the panel, and we consider the corresponding CDS. We take the average, and we have the possibility to estimate capital lambda, so the aggregate systematic default risk. And then we consider a particular representative element of the panel at a certain time, and we consider also the corresponding singular idiosyncratic CDS, etc., etc. And we made this experiment for all the members of the panel. Okay, so this is just a numerical problem, not a theoretical problem. This is just a couple of remarks. Kostas, let me know. What about? 6 minutes. About 60 minutes. Thank you very much. No.
You will hear it soon.
So in 6 minutes there will be the alarm. Okay. So everybody knows how to price a CDS, so we can skip. And just a remark: the idea is that we can extrapolate the information of the parameters of the risk-free repo rate simply by taking the US repo rates information in market data. For overnight, I can take this information from the OIS rate, the overnight rates, and so far so good. Now I would like to deduce some information of the idiosyncratic as well as the systemic lambda from the CDS. That's the idea. Once I disentangle and separately calibrated the corresponding lambda, then I put everything together in order to have a model in which there is also the, if you want, credit market risk information, not just the credit spread, the basis spread information. Okay, so blah, 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 and in the blah, 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 there is the possibility to price CDS in this particular affine framework, which is not surprisingly similar to the pricing of LIBORs and products on LIBORs. Basically, I have to consider a building block, which is the so-called zero recovery loan. So this is quite trivial in the affine case, involving still the solution of the Riccati's. And I can construct the CDS, but I mean, this is standard. This is not really about this model. So the CDS can be seen as an exchange of two legs. And for the no default coupon payments, I have just to deal with this stream of payments involving the zero loan or difference of zero loans, as well as the first element. So the tricky point is the only point where we have to be a bit careful about is the computation of this element involving just a process Z. So the process Z is the expected value of the credit intensity, and I can say something in terms of these dynamics. And the tricky point typically used in CDS pricing is that you can reduce the floating leg in terms of differences of this indicator function involving basically by approximating the story by the differential of the corresponding process Z. But okay, there is not very interesting. There is nothing particular to say, just that, I mean, also in this case, the affine modeling seems to be quite natural as an approach for this kind of problems. Well, so after all, we are able to find the price of the CDS. Here there is no time, and as you remarked, there is no space as well. So I end up with some numerical results. So this is the information about forward curves. There is just a remark to do. There is a dichotomy for products whose maturity is less than 10 years and greater than 10 years. So we decided to just fix and block our investigation till 10 years, because I mean, there is a structural problem in the market. There is a segmentation also in terms of maturities of this kind of products. We have to think about this problem, but for the moment we just keep and keep in standby this problem. So our investigation involves just considerations involving 10 years maturity at most. Well, the idea is that this is the market, in the sense that we have not prices, we have of course bid-ask prices, and in order to calibrate the model is not just a question to take the mid. Here the market may be quite, quite sophisticated, so I would like that my model should be always calibrated in order to fit in the bid-ask spread, okay? So I fix an ideal straight horizontal line, which represents my model, and it should be always in the between the bid-ask spreads. For different dates, so for the moment there is no time series calibration, there are just a cross-section and we just choose a couple of days. This is the first calibration result in terms of the OIS discount factors. So I just take the OIS spreads, and what I see here is that, okay, the fit is not so bad for the two dates we consider, in the sense that the model lies always in the between the bid-ask of our spreads. You see that, I mean, the form of the bid-ask is very, very regular here. This is the reason why considering a mid-price maybe sometimes financially meaningless, okay? Well, there are some irregularities in the beginning. This is quite pathological in the sense that the available products sometimes are not so regular in a very, very short maturity. And this is what you observe, for example, for one maturity. I mean, we are working with abstractions, so short rates. This is quite natural. Okay, this is the incremental utility by introducing three-factor model instead of just one-factor model for describing the OIS dynamics. And we see that, okay, from the qualitative point of view, there is not so much difference, basically. So at least we can have an idea about the parsimony of the model. This is important in terms of the global calibration, because nice idea here is that you can just try with one factor process. You calibrate on this model, just by using repo, just by using OIS, and then you introduce other correlated factors. So basically, the global calibration, which has a huge number of local minima, can be calibrated step by step by a nested procedure. Okay, this is also for the other date, 215, 2000 is better. And this is also for the basis swap data. This is the market as well. I have to consider bid-ask prices here. And this is the result. So basically also here we see that, for example, there is a bias here. The yellow line should be always above. So in the short period, there are some strange effects happening as well as also with 3 factors. So with 3 factors is more regular. But it is that we are globally quite satisfied about the calibration because we are always able to stay in the between. Okay, that's the idea. And for the CDS, there is much work in progress. Now we are suffering a lot for calibrating CDS because it seems that there are some bias in the market. And we are trying to understand which is the potential bias. And there are many sources of bias. It can be an accidental bias, so a bug in the code, not so probable. The problem maybe is really in market data. So we are thinking about the possibility to change dates, but of course, if you have to repeat with a time series calibration, we cannot just close your eyes and cross your fingers. Okay. So sorry about the preliminary results, but still we are working on that. Okay, so also for the other date, the results are very, very nice. Still in standby, waiting for the results for the CDS market. This is the arrow, and the arrow basically is concentrated on the very, very short maturities, but you see here is an excellent fit in general. Okay, so at the end, in the last 3 seconds before the alarm, the idea is that we are still trying to calibrate using CDS also, and there are some preliminary results very, very promising in the sense that we are able to deduce this kind of information for just quoted products, and not just involving non-linear products. There is a natural question in terms of the volatility of our processes, because normally if you consider just linear products, volatility doesn't enter the story, and there's nothing to do with the unspun stochastic volatility. There is something related to the fact that we are just considering linear products. And what is more important now, there are some hedge funds who are exploiting this potential arbitrage opportunity. This is not an arbitrage, this is a statistical arbitrage opportunity. It's just betting, for example, implied against a realized volatility. It's the same. And it seems that the Sharpe ratio, it was a remark of Rama Conte told me that he is in connection with some funds who are dealing with this kind of strategy. It seems that the Sharpe ratio is equal to 2. So it is almost an arbitrage. Sharpe equal to 2 is, it matters in this kind of strategies. So in this framework, we are able to compute also the Sharpe ratio, because we can compute basically everything. So we are very curious to see, as soon as calibration is done, what gives in terms of performance of a potential hedge fund. Okay, I don't want to abuse of your patience. Apparently, there is no alarm, so it doesn't mean that we are safe, but at least thank you for your attention.
Thank you very much, Martino. Any questions? Yes.
Comment, right? So you said you had issues with fitting the CDS. I mean, of course, again, you have liquidity premia there, right? I mean,
sure. One possible source of problems.
So there are ways to handle that. There are papers who actually propose extensions of models so that you can better match the CDS.
I think there is something deeper, so I'm curious to, to jump to you for the same question. What about your CDS calibrations in your paper with...
Yeah, we use liquidity measures.
Okay, and you didn't find any dramatic bias in the estimation of the CDS?
We took the average, right? So that's also helping. And
Yeah.
You do also average. Okay.
Yeah, the problem is that I not only average. For capital lambda, there is no problem. I think that is quite similar to what you did. I have also to estimate or filter out small lambda. So I have to follow an idiosyncratic behavior. And here, perhaps, yeah, one possibility may be risk premia, idiosyncratic risk premia, and aggregated risk premia. It's a mess. It's a mess. So perhaps we have to circumvent the problem. But any idea is greatly welcome.
Anything else? Okay, let's thank Martino again.
Thank you.